Hello and welcome to the first of what is scheduled to be 67 Toddcasts to cover the first semester of organic chemistry. It's just basically aimed to give you the foundations of the course, and I see this uh, kind of as a cross between a textbook that most of us, I think, honestly prefer videos to books in a lot of cases. So this is a video version of a textbook at, in part, and then highlights of a lecture series as well. So what I'm hoping this will do is give you the foundation of organic chemistry, starting with a thorough review of the fundamentals, and then getting into reactivity, certain classes of compounds like alkanes, alkenes, alkynes, alcohols, aldehydes, and ketones. That's what we're going to cover this semester. But the main purpose of this is to give you, if you're taking my class, pre-reading, pre-exposure, so that when you come to lecture, you've seen most material. Or if you're somebody who had my class a while back, this is a good review for whatever you need it for. Perhaps you're preparing for a standardized test. So hopefully it will prove useful. I'm going to keep this up hopefully for a fairly long time on YouTube. And it just before I get into it, just to wax a little nostalgic, this actually will have certain tricks that I did the very first time I ever taught organic chemistry, which was way back in 1989, 1990 at UC Irvine, all the way up to what I'm doing at the time I'm making these, and that's teaching at Pepperdine University. And it's a whole range of what I've learned over the years and hopefully some really useful tricks. So that's what this is. My name is Todd Bennett, and I will probably not introduce myself in all the rest of the Toddcast. So onward we go. So hopefully this will give you a good rundown on just organic chemistry by the time we're done. So let us start. I want to cover in this first one the HONC application, which, just to tell you what that means, that's hydrogen, oxygen, nitrogen, and carbon. And so if you look at organic molecules, they'll be rich in carbon. That's always going to be the case. They're going to have some hydrogens. That'll always also be the case. And then they may or may not have oxygen and nitrogen, but usually there'll be one or the other, possibly both. And then occasionally we'll have a few other elements tossed in there as well. Metals get involved in some of our reactions, but HONC, that makes the core of most of the structures we're going to deal with. And then atom connectivity, organic chemistry, to do well in it, you have to be able to visualize what molecules look like. And that means knowing in your mind how the atoms connect. So you hopefully have had Vesper theory in general chemistry before. So that'll tell us something about the bond angles and the structural shapes. And then something in terms of bonding, how many bonds each atom makes. And so that's what we're going to start with. And so, as is true with any topic, if you can make analogies to stuff you already know, it's going to be easier to learn. And if you realize it's often not the content is challenging, it's just new. And if it looks unfamiliar, it can be daunting. But OChem is a great example of a class that will seem really hard during week one when you're going through it. And then when you're in week two materials seem hard, but week one will seem really easy. It's a really easy class when you look at it through your rearview mirror. After you've learned everything and you're looking back, it's not bad, but as you go through it, it can be very challenging. Lots and lots of material, and we're going to start with the basics. So the preview of the class. To do well in this class, you're going to have to be able to count to 4. Hopefully not that big a challenge, but if you only have up to 3 mastered now, get that 4th number in, you'll be fine. But 1, 2, 3, 4 is HONC, H-O-N-C, meaning the atoms we deal with, again, hydrogen, oxygen, nitrogen, carbon, form 1, 2, 3, and 4 bonds respectively. So hydrogen has just the one electron. It's a 1s1 if you recall from GChem. Having one electron, it would want 7 to complete an octet. That's what we assume, but there's no way it's going to do that. In that first row, there just aren't enough orbitals available. So it ends up, it doesn't really want 7, it settles for 1. So if it can complete it as a shell of 1s2, be happy. So it has 1 electron of its own. If it connects to another atom, that'll be a second electron shared in a bond. So it'll feel like it has 2 electrons, it'll be happy. So it doesn't really want 7, it wants just 1. So it makes 1 bond. Oxygen has 6 valence electrons. So if you recall the electron configuration, 1s2, 2s2, 2p4. So in the second shell, then equals 2 shell, you have s2p4, so 6 valence electrons, so once 8. So it has what's known as a lone pair and a lone pair, two electrons that are just going to stay in their own orbital, they're not going to be shared. Then it has two single electrons that each want to form bonds. So it has 6, wants 2 to complete its so-called octet. So octet rule comes from S2, P6 for whatever row you're in, for 8 electrons total. So everything wants to get up to 8. And so oxygen starts with 6, makes 2 bonds to get its 7th and 8th electron if it can bond here and bond here. Nitrogen is 1s2, 2s2, 2p3. So the second shell again is valence. And that's an s2p3, so a grand total of 5 electrons. 1, 2, 3, 4, 5. So it wants 6, 7th, and 8th. So it's going to form 3 bonds. And then finally carbon. Carbon is 1s2, 2s2, 2p2. So the second shell, the valence shell, has 2 s's and 2 p's for 4 electrons total. It wants 8, so here it's 4, 1, 2, 3, 4. It's going to form 5th, 6th, 7th, and 8th. Has 4, wants 4. So in stable, uncharged structures, you will see hydrogen making 1 bond, oxygen making 2, nitrogen making 3, carbon making 4. If they ever make a different number than this, then it's going to be a less stable structure, and they'll have to account for a charge or some sort of electron deficiency. So for now, just recall HONC, 1, 2, 3, 4. 1 bond, 2 bonds, 3 bonds, 4 bonds. If you remember this, you'll be in great shape to start out with. So we refer to making 1 bond as monovalent. It wants to pick up 1 electron in its valence shell. Oxygen is divalent, nitrogen is trivalent, and as you probably are seeing this trend happening, carbon is tetravalent, meaning it wants to make 4. But just remember, HONC, 1, 2, 3, 4, and that'll help you out. So if you can count to 4, you're on your way to doing well in OCHEM. So the covalent bond. Covalent bond is what we're going to focus on in organic chemistry. In general chemistry, you probably dealt with ionic bonds where you had a cation and an anion, where you had a full electron transfer from, let's say, a metal like sodium, for instance, would transfer it to chlorine to make it chloride. So you'd have Na plus Cl minus. We have no ionic bonds in the majority of our organic molecules. We may have ions, and so we'll get to that at some juncture, but for the core of our molecules, it's going to be sharing of electrons for covalent bonds. So if I draw water, if you recall, hydrogen has 1, wants to make 1. So you get 1 bond right here. Hydrogen has 1, wants to make 1. So you get 1 bond there. From oxygen's perspective, you have 2 lone pairs, 2 4 electrons, a 5th and 6th to begin with. Picks up the 7th and 8th sharing. So you end up with these bonds. So let me go ahead and get rid of my green line and say that this is typically the shorthand for how we show it. So when it's 2 dots, it represents 2 electrons in what we're going to call a lone pair. So those are lone pairs. And then the line represents a bonding pair. So everything for stable chemistry is going to deal with pairs of electrons, bonding pairs and lone pairs. You're going to hear these terms repeatedly. Okay, so let's consider, again, our atoms. We had an H and an O. Now let's consider H, N, and C. So again, HONC, H, O, N, C, the common elements. Hydrogen has 1 electron, wants to make 1 bond. Hydrogen has 1 electron, wants to make 1 bond. Carbon has 3 H's here, so I should have drawn it out. So this actually represents a dot here, H, and H, and an H. So I'll draw it. It'll be drawn out in the future slide, but that's what this represents. So I'm going to just ignore this and put H3. We're going to see that shorthand a lot. But from the nitrogen's perspective, once make 3 bonds, so it makes 1 to an H. He's sharing 1 electron to make a 2 electron covalent bond, 2 electron covalent bond, and 2 electron covalent bond. So there they go. They come together and line, line, line. Okay, and one more. Let me get rid of my most recent writing. and say that this group here is the same thing as it was here, the CH3. Carbon has no lone pairs. It has 4 individual electrons. So it's going to form one bond to H with one of the electrons, another bond to this H with this electron, one here with this electron, and finally this CC bond. They come together, no lone pairs, so everything is halon. So bonding pairs are also here, 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 and here. Nitrogen has a lone pair and 3 bonding pairs. Okay, so this isn't that tough, and you probably have done this, but just reacquaint yourself with it. Again, hang on to the HONC rule. HONC, 1, 2, 3, 4. H makes 1, oxygen makes 2, nitrogen makes 3, carbon makes 4. Oxygen also is a pair of lone pairs. Nitrogen has a single lone pair. On structures, when you draw them for exams, you have to show your lone pair of electrons because it's important in terms of stability and reactivity, whether they're there or not. So get in a good habit of always drawing carbon with 4 lines, nitrogen with 3 lines and a lone pair, oxygen with 2 lines and 2 lone pairs, hydrogen with just a line. Okay, so let's go ahead and practice. So I want to get good at seeing a formula and drawing the connectivity. So if you see a formula such as H3COH, that means this molecule is made up of 3 hydrogens starting from the left, to a carbon, to an oxygen, to an H apparently on the right side. So we draw it this way sometimes. Now you might see this as H4CO. You might see it as CH4O. Different ways to draw it. But this one helps us a little bit by telling us sequentially the sequence they're in. I'm going to do a whole bunch of different ways. The book does a bunch of different ways because you never know who's writing it and what their preference is. But this is one where from left to right. So let's go ahead and figure out how to make this molecule. It is easiest to start with the element that forms the most bonds because that's got to be in the center. For hydrogens, they only make 1 bond, so they're always going to be at the periphery. They're always going to be sticking out the end of molecules. Whereas carbon, because it makes 4 bonds, it needs to be in the middle. So start with a carbon. I'm going to put its 4 lines in there. So 1, 2, 3, 4. This isn't necessarily the way they exist in 3-dimensional space. It's just for drawing structures in a quick and convenient way. I'm going to put a carbon with lines at 12, 3, 6, and 9 o'clock. Okay, then I'm going to go and pick the atom that has the next most bonds. So HONC, carbon has 4, nitrogen would be next. There's no nitrogen. Oxygen is next because it has 2. So add in the non-hydrogen atoms because they make 2 bonds. So I've decided oxygen to go here. I could have put it any spot. It didn't matter. Just easiest because I want to kind of follow the way the structure is drawn here. But if it was up top, down here, over here, it'd be the same thing. So now we have a bond between carbon and oxygen. And I have now 4 hydrogens. And luckily there's 1, 2, 3, 4 ends to various lines. So fill in the hydrogens after that. And the final thing I need to do, make sure I've accounted for lone pairs. So carbon and hydrogen, no lone pairs to worry about. Oxygen has 2 bonding pair, so 2 lone pairs to complete its octet. So add in the lone pairs. If you forget to do that, you'll lose a point or so on exam question. Okay, so systematically, start with the central atom, carbon, 4 bonds. Nitrogen would go next, oxygen next, and then hydrogen last, because you want to build from the middle out. So draw the bonds, add the non-hydrogen atoms, then hydrogen atoms, fill in lone pairs, and you got a structure. So this one's a little more complicated. Again, I'm going to read from left to right. So 3 H's on a carbon connected to an O, connected to a carbon with 2 H's, which is then connected to a carbon with 3 H's. So let's draw our central atom. In this case, it's going to be central atoms with the 3 carbons. So I've left the space, I've kind of put it C, C, and C. So C, C, and C with room for the O that's in the middle there. So let me go ahead and draw 4 lines around this one, 4 lines around this one. Ends up this line here is going to connect. So I have 1, 2, 3, 1, 2, 3, 4. I'm sorry, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. But I have a bond already formed between that electron and that electron. Okay, so I started my central atoms. I drew in all the bonds. Next, the non-hydrogen atom, no nitrogen, so oxygen's next. Oxygen can make two bonds, so it's going to fit in that hole perfectly. Now I need to draw in hydrogens. There are 3, 2, and 3. So 1, 2, 3, 1, 2, and 1, 2, 3. Perfect. So in every one of these bonds, there's 1, 2 electrons, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. Okay, so everything's happy. So last thing I need to do, add in lone pairs. Only oxygen has a lone pair, so we're set. Not bad. Okay, so what if they mess with me and they give me a molecule that has multiple stage 3 groups? Oh, that's no big deal. But now sulfur instead of oxygen, nitrogen, hydrogen, and carbon. So occasionally you will have other atoms to deal with. Sulfur is located below oxygen in the periodic table. So I went to this column, I have oxygen there and sulfur there. So they are both S2P4, meaning 6 electrons. So they're each going to ideally make 2 bonds. Sulfur, because it has the ability to access the d orbitals, can actually have an expanded octet and have a 5th and or 6th electron pair around it. Again, this is hopefully something you learned in general chemistry, so this is a reminder. But for simple organic molecules, we're just going to see the sulfur behave just like an oxygen. So HONC, carbon's my central atom, makes the most bonds. So I have a carbon here, but I also apparently have a carbon here and here. So let's see. I have 1, 2, 3. I don't know if they're in a line. We'll figure it out, but I'm going to start with a line and see if I got it right. So I now have 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So looks good. I'm going to add in sulfur. I can put it anywhere I want. Doesn't matter which line I put it on. I am going to try to get ahead of myself and think that, okay, if these are CH3s, this carbon can only fit 2 H's. These can fit 3 H's. So sulfur probably has to go on that center carbon. So I'm going to put it here, and just like oxygen, it makes 2 bonds, and then fill in my hydrogen. I have 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, and then the other 3, 6, 7, 8. So there they are. So 1, 2, 3, 4, 5, 7, 8. And then lone pairs. So just like oxygen, sulfur is going to have a pair of lone pairs coming in. Okay, this comes with practice. I'm hopeful, and it's always going to start out this way, that this will be easy eventually for you. But at first, it just isn't. At first, you have to go through the practice. As simple as this may seem, it is really important to make sure you get this down pat. So draw various structures when you have time. The book has a lot of examples. We'll go over some in problem sessions. We'll expose ourselves to it. So again, if you know why, it'll help. But hydrogen has 1 valence electron, so it only makes 1 bond because it only needs to connect to 1 electron. It doesn't have enough to share otherwise. Oxygen has 2. Nitrogen has 3. Carbon has 4. So it's really just a case of completing the octet. Hydrogen doesn't have an octet, but nitrogen, oxygen, and carbon do. Hence we call it the octet rule. Everything in the second period of the periodic table wants to get an octet. So second row elements. So anything from lithium through neon. The reality is doesn't really work very well for lithium, doesn't work for neon, or works all the way you get over to neon, but it doesn't work before that. Okay, so here's our table. Here's our big picture of how things connect. Carbon, we're going to eventually learn, again, 4 bonds, 4 electrons. But in 3-dimensional space, this is getting ahead of myself, but it's going to form what's known as a tetrahedral center, where it will have 4 single bonds. Sigma bonds is what they'll be called, where one goes up, and then 109.5 degrees down here will be another one here, another one here, where all the angles are 109.5. It also can form what's known as a double bond, two bonds of the same atom. So it'll have a single bond, and a double bond. So it's still four bonds, but it has a double bond. It can also form a single and a triple. And if you want to get really fancy, it can form two double bonds as well. Okay, so it's going to form four bonds. Nitrogen is going to form three. So notice all I did is I took the structure up here, got rid of this bond here, and made a lone pair. Got rid of this single bond here, made a lone pair. Got rid of that single bond and made a lone pair. So nitrogen is going to make three bonds, whether it's three different atoms with single bonds, two different atoms, one double, one single, or a triple bond. Oxygen makes two bonds, either two single bonds or a double bond. And this dash here, I really didn't have to do it. I just want to emphasize that it is a three-dimensional structure like this. So basically what I did is I just took nitrogen, got rid of the one I'm erasing up there. So if you just get rid of that one bond, it'll be this structure. But we won't draw it that way. We will almost always draw it as that structure with straight lines, which just emphasize that it's the same thing as above, but one of the bonds, sigma bonds, turned into a lone pair. And then finally, hydrogen just makes one bond. That's just what it does. Okay, so we have finished the first electors. The Toddcast will be really mellow for the first few, and then eventually we will get to a point where they get a little more intense, but hopefully this is all review for you. So thank you for joining in, and I will see you at the next Toddcast. Until then.